Hola, muy buenos días. Hey, welcome everybody. How are you? You're okay? All right. So let's roll. This is about Edge Native, and maybe some of you have an idea of what Edge Native is. I don't really. So let's go and try. So back in 2010, everybody started to move to the cloud. We really saw the pendulum swing all the way from, I have all my stuff on-prem, let's go and move it to the cloud because there all the beauty happens and it's so simple. And well, by 2015, roundabout, we had a load of customers, and some of the people are still swinging over that way, right? We had loads of customers in the cloud. And then when they were in the cloud, they discovered that the cloud, despite that what some people told them, is not for free. So for instance, we have a company that builds software for autonomous vehicles. And an autonomous vehicle in development creates roughly 4 terabytes of data a day, roughly 200 gig an hour, from all the sensors, all the video sensors, and what have you. And in order to analyze that data, yes, there is 5G. You could go and eventually move it to the cloud and get it processed. But there is also this little bit of a bill that you need to go and pay, not only for processing in the cloud, but also transporting all the data. So for certain use cases, it's really not possible to even move it to the cloud. So cost is one argument. The other argument I think that everybody is swinging is obviously performance and latency, and Roland make a good case. Like, if you're on the shop floor, you want the bloody robot to react immediately and not in 200 milliseconds because the message is in transit to California and then back. And then finally, I think another argument that made it kind of swing back is, how do you call this these days? Macro politics or local politics or regulations, or I want to go and keep my data local. For instance, if you are operating a pipeline and you're something that the pipeline guys call midstream, is really the guys that observe the pipeline, the data that observes, or the sensors and all the processing locally, that looks at the pipeline, which is a fragile thing as we know these days. This data must not leave the premise, not over their dead body. So there is a load of regulatory that you need to go and factor in along with all the security things. So which is why some people don't really see the swinging back. And one big thing why it's also swinging back is, and Gartner echoed that recently, is some 2 years ago, if they talked to people about Edge and ML, AI, hardly anything. These days, around about 30% of all their conversations about Edge include ML, and they expect it to be 100% really shortly. And there's a big reason for that. And this is this. These guys created chipsets at scale for everybody to go and make local AI really economically viable. If you look at what a mini TPU from Google costs you today, it's less than $100. If you could go and buy it, right? Supply chain aside. You can't even buy a Raspberry Pi, as mentioned earlier on, at a decent price anymore. But when we do this, right, so everybody swang to the cloud and loved the cloud, and now we're on our way back. We like the experience. Can we keep the experience? And I think that's what I would call Edge Native. So can we keep all the learnings that we had there and maintain it? But yeah, Edge, which Edge? Your Edge might be my cloud. So let's go with the Linux Foundation taxonomy, because I think that's quite helpful. So they have this thing that starts all the way from centralized data centers out here, which is clearly the cloud, all the way to constrained device edge. And what I'm actually interested in focus on is what we call the smart device edge, and from a Linux Foundation nomenclature perspective. Smart device edge is something that is user-facing client compute. What's that? Who likes coffee? Who likes burgers? Okay. So you're going to go and operate not one burger restaurant, but maybe 1,000. And you can pick your favorite chain. And you're going to go and operate not only one coffee shop, but maybe 10,000. again, pick your favorite chain. There's quite a few. You're a store owner for multiple of these stores. And your job will be to, in these stores, whether it's now your burger restaurant or your individual coffee shop, what you need is something to go and display the latest menu on a screen. What you also want to go and do is play music in all your restaurants. What you also want to go and do is kind of do queue management across the cashiers and open up another cashier desk if, well, there is demand. What you also want to go and do is, at least until recently, check whether all your people in the restaurant have their face masks on. What you also want to go and do is do inventory management of what you have on the shelf in the supply room. So there's loads of little apps that you need to go and run. And you need to go and run them locally. And you need to run them in an environment, and that's again to Peter's point earlier on, in an environment that is a little detached. So we have one large customer that has 2,000 locations, neither burgers nor coffee. They do chicken. And around about 1% of all these locations are down at any point in time. It's not always the same 1%, obviously, but they're all, well, spottily connected. So that's the operational environment that we're targeting. And that's an edge where you can't really do the same principles that you had with the cloud anymore all the way to the edge because they're slightly disconnected, they're air-gapped, and they're operated by people that are clearly non-IT people. The best thing that you can go and tell the local guy in the Starbucks box or in McDonald's or whatever is switch it off. Or there is this red thing called factory reset. Go push it now. That's the maximum debugging. So you can't really say, well, I'm running a local cluster. Please kubectl in, and then you do. No, bummer. Again, talking Gartner. Gartner did this nice split. They call this either cloud out, where you can go and use the cloud principles to a certain extent and just extend the cloud principles further out. So you're operating your local data center and what, say, the Metro Ethernet, for instance, calls the Metro Ethernet Edge or Metro Ethernet Edge computing and the likes. All of these things are kind of an extension of the cloud. You can still treat them as a regional zone. That's easy. We can go and use these principles, but what if we have these things that are massively distributed, hardly really attached to the network all the time, and if they're attached across multiple of these things that Peter talked about earlier on, middle boxes. They filter, they firewall, but one thing for sure is they screw up your traffic. And you might be able to reach the internet from any local shop that you or he operates, but it's very unlikely that the internet is going to go reach you. So we have to go and work with these individual principles, and it's all about location. Also, where you operate, whether you operate your shop in France or in Spain or in California, local regulations might be very different, so you want to go and adhere to those. So let's go and look at some design principles, and I want to go back roughly a decade in history and to something that we all remember and that is still stable, which is 12-factor. So the Heroku guys did us a great favor back in 2011, right? So Adam, Peter, and all the Heroku crowd. They gave us the 12 factors, and if you look at these 12 factors from code-based dependency, config, backing services, and the likes, they are very stable. So these principles still apply, and that's quite an achievement, I have to say, in a world of software. Building something that is stable for 10 years, go ask OpenStack. Maybe ask Kubernetes in 5 years' time. But we have to go and slightly rethink or maybe reinterpret some of the 12 factors, and that's what I want to go and briefly chat about, if we apply these things to the edge. So from a dependencies perspective, there is dependencies and policies that we have to go and factor in. And dependencies and policies are now also with regards to where I am, not only what I depend on. Because in the cloud, everything is like next door. If you're local, then nothing is next door anymore. From a backing services perspective, it's not only about the services, but also where they are. From a concurrency and scale perspective, you're scaling slightly differently because you need to also scale out across the number of locations suddenly, and not only with regards to your workloads and processes. Disposability, yes, we have to again reinterpret that. We want to go and kill any process any point in time, but we also want to go and kill a location any point in time. You can't really rely on that everything is still working, because that's again something that I found. Like recently we had an outage of a switch. And you know why that outage happened? There was a technician doing something at the rack nearby. And the switch was so noisy, he switched it off while he was operating on that one. It was just a switch for voice relay, not important, right? He couldn't call anybody at the same time. And logging is also an interesting thing in that scale. So if we look at concurrency and scale, that's the one-to-one picture, 12011. So we scale with running processes. If we need more, you increase your replica set, right? Fine. Now, if we're thinking of, we need to go and run in 100, 1,000, 10,000, maybe 100,000 locations concurrently, pretty much the same thing, because you basically want to go and play the same music no matter where you are in some local coffee shop in Malaga, right? So we have the scaling from a sites perspective, from a locations perspective, as another dimension that we need to go and factor in. And for me, sites are just an abstract notion of location. It can indeed be a physical location, but it could also be some local grouping. So everybody in the dev team, everybody in the marketing team could indeed be something location principle. Because end of the day, location can be physical, but the cloud can be just another location. So in that term, then, if you really want to go take it to the far end, the cloud is just another edge. Bummer. And we deploy applications to sites, to that particular abstraction. We don't really deploy an application to a particular node on a site. Because again, if you're the store manager, you want to run it in the corner across the street from the port in Malaga. Whether it runs on this computer or that computer or that computer, you don't care, right? So at least you shouldn't care. If you care, then you're probably an IT guy and not a store owner anymore. And from a disposability perspective, the robustness now goes by site. And we need to go and see these things as, well, any site is kind of cookie cutter. So if you think of a site as a cluster, yes, your cluster now is cattle. You can go and kill cattle any point in time. So they're no longer pets like we do them in the cloud. Sites are cattle. You can kill them, and you can restart them, and hopefully they rebootstrap themselves into the state that you want. So it needs to be 100% decorative. Otherwise, you're ending up with this thing like, how do I debug this site? The answer is you don't. If we have backing services, yeah, the principle is the same, right? So we have a production deploy, and it has dependencies on individual services that we're explicitly declaring. From our site deployment, we do the same. We just say, well, this particular site is autonomous in its deployment. It can go and also pull things at its leisure, and it will pull it from declared sites. Maybe from the internet, maybe from next door, maybe from a nearby node. You want to go and declare these things, and they have a principle of location in there. Coming back to something that Peter said earlier on, the connectivity between site and the cloud is really loose to that extent that you can't really rely on it. Anything can fail at any point in time, and don't assume that the cloud can reach the site. There's typically multiple of these middle boxes in between, and you don't know what these middle boxes do. We talked about earlier on that Cisco might fix the problem of net traversal. Yes, there is RFCs out there for stun, turn, ice, and whatever, and all of them have that principle like, yeah, you can go and punch holes, you can go and discover who this guy is externally, You can try to maintain the pinhole. All of that requires doing something special for an environment that you don't control. Don't do something special for an environment that you don't control. Just rely on, I might be able to reach the cloud at every now and then, but I might not reach it all the time. For sure, you don't want to go and maintain a tunnel. That's even harder, because maintaining a tunnel means keeping the pinhole open all the time. All you can do is pull artifacts from the cloud, and maybe you can go and push telemetry information. So state, logs, metrics better. Metrics, logs. And I think this is where we really need to evolve. Back from 2011, I think we all did that by now. We moved from logs, in most of the cases, to metrics. That's at least what Cisco has done for its routers. We try to go and give devices counters, as many as we have, right? I think we have millions of counters for a particular device. And we only want to go and retrieve these logs if we really want to, and then do that on demand very selectively. Because we have one famous thing with one customer. He turned on logs, and it was the last thing that he did. Because all the bandwidth was gone, right? And so metrics can help you, but the thing what you want to go and focus on is actionable metrics. And that's a real problem. We want to go and send information and not data. So how do you filter that out? If you have a pool of 1 million, what is relevant at a given point in time if you see some change point? And we're going to go and briefly chat about that particular problem later on, so that the device is able to go and auto-filter and only upstream what really matters instead of sending data, because you might not have the bandwidth for sending data. And one final point, like declare your dependencies. We want to go and declare our dependencies like we did, between sites, within a site. And as we declare dependencies, also factor in policy that might go with that dependency. Because you're suddenly starting to rely on things, and you might be able to enforce the things that you rely on. And what we found is that, especially now with all these regulatory things being kind of raining on us, they're piling that stuff on us, and we have to go and rebuild this and reforce this into the system, much like we did security in the past, much like we did observability in the past. We need to go and factor policy and regulatory into the system at coding time. So you want to go and build and instrument your code, much like you instrument it for observability with something like open tracing, open telemetry. You want to do the very same principle, build in hooks so that you can go and later on apply policy to these hooks. So that's something I think that we have to go and evolve as an overall principle. Much easier to later on apply. So taking everybody's favorite darling or not, let's take Kubernetes as an example to apply these principles. And just from a schematic perspective. So if I'm oversimplifying Kubernetes, it's an API server that allows you to put stuff into a database, and then you have individual workers fetching the state from the database and realizing that state. So this overall thing is a pet for you, and then the workers are cattle, right? If we apply our principle and saying, well, let's go and have disposability and backing services and the sites as edge clusters, the clusters can now fail at any point in time, our cattle. So I can go and do clusters of clusters, and there's quite a few solutions out there that do this in one way or the other, sometimes not all the way that way. But yeah, you have an API, you have a database, hopefully a reliable one, and then these individual sites become like one cluster, maybe multiple clusters in one particular site, but treat them as cattle. And treating them as cattle means you want to go and scale that out, and you want to have these guys be able to pull state from a centralized repository. And you see that design principle starting, at least in many of these fleet management solutions that they're being rolled out by a variety of companies right now. So you have something that I would call an edge operator. Some people call that a different operator, but there was mentioning of a variety of companies even earlier on that do these things where you retrieve state from a centralized database and you push information up. what you shouldn't believe is that people still build tunnels from here to there or try to maintain the tunnels. I'm not a big fan of that, because that makes the overall thing relatively fragile to maintain. Then you're going to go and add dependency and policies. You need to go and be able to schedule at that level, because you need to be able to decide what goes to which particular site, because you might not want to have everything to every site. You might even want to go and split workloads between sites, and you need to go and factor in the compliancy pace. So relatively straight up. Let me give you a couple of examples on what this feels if we're building stuff for the edge. And I said earlier on, like, following the Gartner mantra, like, ML, AI, and edge is kind of a match made in heaven. If you make this match made in heaven, maybe if you're matching, then you still have to go and consider certain things. So we want to go and swing back and run AI workloads all the way at the edge. Because right now, most of that AI stuff is running in the cloud, 96%, at least that's what people say. We love the tool chains. You can go and build it, and whether you build it with, well, the A tool chain or the G tool chain or whatever, I don't really mind. You have an outcome, and the outcome is a model. And then you need to go and run it in an environment that eventually is built out of what was mentioned earlier on of Raspberry Pis or smaller devices. Might be even smaller. You might run it even on a video camera or the likes. And you run it in an environment that has eventually spotty connectivity. You might not have 10 gigabytes between all the individual devices, and the devices might be so small that your model is too big to run on an individual device, or it might be too low performant to run on a particular device. So let's say I'm a happy developer. I created an AI model, and I actually created two. So I have my AI model all done. It might be, say, TF-Lite, Onyx, what have you. The first one requires 100 meg, so it's a really beefy AI model. It doesn't fit on my individual compute node. Bummer. And I have the second one, and it fits, but it runs at 2 frames a second, but I need 5. Use case for 5, you do people detection at the front door, which is, again, something that you might want to go and do in your coffee shop, or I think you were the coffee shop, you were the burger restaurant, right? Correct. Yeah, you don't really run with that performance, and if you're running with too low a performance, you might miss people. So at certain areas, like, you want to go and be a little quicker than, say, a single frame a second. And 5 frames a second is a good measure where you're no longer missing people, for instance. And for that, yeah, well, you need more performance. What do? What could you do is, yeah, well, you buy more expensive hardware. Buying hardware today is virtually impossible. Try to go and buy Raspberry Pis on Amazon, fail. Try to buy Jetson Nanos on Amazon, fail. Try to call your favorite vendor and twist his arm, maybe he has a few, right? The other thing is hardware acceleration, okay, check, we can go do that. The second thing is, obviously, we can go and compress for our use case. So we can look at the generic model that I built in the cloud and then say, well, do I really, for my use case, need these layers? Probably not. I can go and remove them. I can quantize the individual values that I have in the model down to, well, a few, which is, well, a great reduction in complexity from a computational perspective, so you can really get 10x out of this if you compress properly. And the final thing is, like, yeah, well, most of the people here are here talking about distributed things. Yeah, it's just go and split and conquer, right? Divide and conquer and distribute things. So we can also split and load balancing, which is relatively new, and we've started to experiment with that. So if you have an AI model, and the AI model is a relatively simple one that you have, say, for instance, with MobileNet or the likes, you quite frequently just see that these models only have forward references, and you have natural split points. So if you have more parallelism, it's harder to split, but you can still split. So let's divide these things and then, well, run one portion on one particular node. We can go and animate that a little. We run one portion of the model on one particular node, then communicate the individual weights and findings from this particular layer over to another node, and then carry on. And you can obviously see that this very likely allows you to speed up. But there is a problem in between. When we found that in most of the cases with most of the models that we've been playing with, this link needs to be at least gigabit, because these models communicate quite a bit between layers in most of the cases. But if you have a relatively beefy local network, it will work. If you try to go and push this over something what was mentioned earlier on, like BLE or the likes, it might be more constrained. So I think the network itself will also play a major role. Well, not a surprise if this is found by a networking company, right? But just go and give you an example of what you can go and achieve. If I'm running, and this is a very stupid detection, and maybe next time I can go and create a better example, because we're detecting what we see on the screen, and what we see on the screen is just watching a monitor. So this guy is running a TF-Lite model on a single node, and it's running at roughly 3.5 frames a second, as you see, and it's detecting that it's a laptop computer. Apparently, it's not a laptop computer, it's a proper monitor. If we split this model and run it across 2 nodes, yeah, the speed up is, as you would imagine, kind of twice the performance. So we can go up to 7 frames a second by just using another node and splitting the model across 2. We're able to execute at the speed that we ultimately want, at least 5 frames a second. And sometimes I can go and play with the underlying runtime. So if the node allows me to use a more efficient runtime like Onyx, compared to TF-Lite in that particular case for that model, I can go even further. And this goes to the diversity of hardware that you might have in an edge environment, where not all nodes might be the same nature. So you can go and run a portion of the model on one node and a portion of the model on another node, and you can even split this thing across different types of underlying runtimes. How do we do this internally? Right, we first convert everything to Onyx, and then we apply it, because Onyx is kind of a meta structure, to go and apply it to individual runtimes underneath. Yeah, thank you. What does this allow you to do? I think historically, you had to go and do a trade-off between accuracy. So I choose a simpler model in order to achieve higher frames a second. If I can start to distribute AI models, I can achieve the same set of accuracy that I can achieve with a particular model without really compromising on accuracy. So I can move forward on the FPS range by just throwing more compute, but distributed compute at the problem that you might have. Another rant about like edge-specific things, and I mentioned that earlier on with the logging thing, right? By now, everybody understands that logging is avoided by all means if you can. Only use it if you have to. Use metrics, but if you use metrics, you still might have loads of metrics. And I said that earlier on, right? We turn on logging, and it was the last thing that we did. An example from boxes that we build, like routers. If you look at a recent OS, we have around about 126,000 different types of counters. And this goes like, that counter might be number of bytes sent on a particular interface. So it goes by the number of interfaces that you have in a box. So it can easily have millions of counters. And what you get from these people is like, yeah, well, you gave me all these counters, but which of those matter to me? And then you get the typical consultant answer back to the customer, which says, it depends. It depends on your environment, it depends on your setup, it depends on what happens in your network, it depends on your protocol configuration, it depends on so many things that you don't understand. They don't want more data in the backend system than they can go and handle, because if you have 1,000 of those or 10,000 of those, you easily saturate multiple Kafka buses very quickly. So that's not the way to scale that problem. So they want to go and only be told of what really changes. And just a simple example of what this looks like, if you just plot it out, and that goes back to the second keynote that we had yesterday. If you visualize, you can visualize it that way, right? So every individual counter plotted. Do you know what's going on here? Me neither. I think I know what's going on because I put the example in. But so it's really high dimensional, and this is only 5,000 out of the 100 or 200 million that I can go and put in there. It's a multivariate problem. It's really high dimensional. And all these counters are different in nature. They have different units, different behavior, and they interpolate differently. And you can say, well, just focus on the ones that change. Bummer. Out of 5,000 counters, roughly 3.5 change all the time. because they are counters. So that's not the problem. And even further, like I put a couple of changes in, like shutting down interfaces, creating and enabling BFD sessions, bidirectional forwarding detections for routing protocols to go and detect fast failures. Even at these change points, like if an event occurs, you might have fewer changes than if no event occurs. So that's not as simple, right? So what we need to go and do is we need to go and look at all the data. And luckily, the data clusters, we will find that, because inherently, the data is low dimensional in nature, even despite the fact that we have loads of counters. And then we need to go back and say, well, which of these really matters? And because then I can upstream the counters that really matter. So I'm sending information suddenly instead of data. And I'll need to all do that in an online way and very cheaply. So as I said, the data clusters, what is this? This is a projection of high dimensional space onto 2D using T-stochastic neighbor embedding, or T-distributed stochastic neighbor embedded, T-SNE. UMAP gives you similar examples, results. So every single point here, and I can go and plot you the journey, if this renders. Yeah. Every single point here is the system state at a given point in time. And what you see is that the system is behaving like it's relatively stable for quite a while, and then it jumps, and then it's stable again for quite a while, and then there jumps. So there seems to be transitions happening in the system. And this is across 5,000 data points. And if I now put in what really happens underneath, I put events into the system, and they really correlate with these state transitions. So I need to go and factor out what happens here, and can I go and describe this unsupervised in an automatic way without throwing a load of compute at the problem. And yes, I can go and do that. So if I look at a particular timestamp, out of all the counters that change, I can elevate those counters that really change in an automatic way. And the algorithms that we run give us here, like, the most important counters out of the 5,000 seems to be something like session state, count up and count down from BFD. And indeed, we killed the BFC session at that particular point in time. So how does this work in a mental state, and how do you do this? Just to go and give you an idea, what we do in order to go and do change detection is we look at a window in time, and we create a linear combination of this window in time, and then if you see a new point coming in, we look at the angle between a linear combination of the past and the new point coming in. And if this angle is starting to grow, then there might be something going on. And we don't take a single point, but we take in multiple points. So you're comparing the angle between one matrix and another matrix and looking at the principal angles and seeing what happens there. And that's good enough as a change detector. And once you have this, you're applying like, what is the amplitude of the individual counters that you've seen, combined with kind of a measure of how descriptive is a particular counter. And we're applying concepts that are very similar to what you find from, say, typical document scanning to understand what is the importance of a particular word in a particular document. So TF-IDF type behavior we're applying there in order to go and get to the description. And all of this can be done with very, very low compute. To sum up, we can go and get to a cloud-like experience at the edge and enable a transition. Because what you had in your Starbucks, or sorry, in your coffee shop environment or your burger environment is you had a load of point solutions right now. So one thing for one thing, and then you had another vertically integrated solution, and another vertically integrated solution. And the minute you pile up all these solutions, it becomes unmanageable. If we're taking the cloud principles all the way to the edge, we can suddenly, in these environments, even in these really remote environments, we can start to platformize. So we can go and put a platform in. And I think that's really the transition that we're seeing, where the edge, with certain tweaks, can be operated like the cloud. And we can go and give all the benefits to these people that so far said, yeah, well, I need to go and contract a particular company for giving me a particular solution, and then next problem, next company, next solution, and it does not scale. And with that, thank you so much.
So I'm talking like out of ignorance because I don't know, just my feeling is like, is this what we are talking about the edge like a general solution for most companies, or is like something very specific? Because what I feel is that this is like adding a lot of complexity, and maybe it's not worth to chase if you don't have a very specific scenario, or maybe it's worth in any case.
Yeah, is it worth any case, or are we building another aircraft carrier? Very good point. So I think there is this balance. You want to go and apply something that you're known to an environment that is a little more fragile than what you're known to, and that has everything that is very specifically tied to location. We can rethink everything in order to go and build out a solution that is very specific to that environment where things starting to be really edgy and difficult. Or we can go and try to use the principles that we have and tweak them so that we don't really have to learn everything from scratch again. And I think that's my point. And I've seen this a couple of times in the past where people applied the wrong thing to the wrong problem and arrived at a good solution. I think the best example that we all know is Linux. It was not really up for the job at the very beginning, but we made it up for the job. Previously, it was clearly better back in the late 90s, but what won was finally that there was momentum, there was community, and there was people that knew how to use the hammer and the associated nail. And they started to go and use it. And what you see in these kind of far edges out there is there is a load of super pragmatic people. And I think this pragmatism is driving them to use a tool that might not be 100% accurate, but you leverage what you have in a slightly modified way so that you're still able to go and use most of the principles that you're used to, if that makes sense. So it's still maybe too big of a ship, but we're all driving too big of a car. At least most of us, probably. Sorry.
Hello, thank you for the presentation. It was nice. I have a question. Is like you have been talking. I mean, the edge is a concept or is a principle, but is there any tools or framework or something going on already that can help us with this implementation?
Yeah, the answer is yes. Of course, there's implementations. There is a variety of projects under the roof of mostly Linux Foundation Edge, not so much within CNCF, because they created a forum dedicated for that. So there is these open UART super edges, ranchers. You have a bunch of fleet management solutions today. None of them go to the extreme of what I was trying to go and hint at, where you're avoiding some of the complications. You might see additional changes in the future. So this is a little bit like a forward reference. We're working on applying these principles. Have we published code yet? No. Do we have code? Yes. Yeah, but I think we're working towards that. And then you see other companies really following the same design principles. Like I mentioned a few, I think recently there was a blog post from Section. They're heading down exactly that same path, right? So where you're looking at the clusters of cluster principle and making these clusters more autonomous than kind of still trying to treat them as pets. Because I think the treating as pets, being able to kubectl to a cluster is inherently wrong. Thank you so much. And